Hi everyone, and thanks for the intro and thanks for coming to my talk. So my name is Martynas and I work at Isovalent, a company behind the Cilium project. So we work with biggest probably and most sophisticated Kubernetes users, and we help them to network and secure their clusters. So all the work which I'm going to present in this talk is going to be done in the scope of the Cilium project, which is an open source CNI plugin and also network security plugin. And all this work which I'm presenting has been done together with Daniel Borkman, Thomas Graf, and Andre Martins, and other members from the Cilium team. So this talk is about getting rid of Kubeproxy from Kubernetes and removing Kube in a way that we can still have this Kubernetes services functionality. So removing Kubeproxy has one nice advantage, that Kubernetes can finally get rid of Iptables and NetFilter. And those two are legacy technologies which were built over 20 years ago. So NetFilter is a packet processing framework in the Linux kernel, and which is used by Iptables and IPVS. And Iptables and IPVS is used by Kubeproxy to implement the service abstraction. And Iptables or IPVS is used depending on the mode in which Kubeproxy is running. So before we start getting into details, I would like to show you some demo. So hopefully it's working. So I have a little Kubernetes cluster and I have some pods there. So it's Nginx pod 1 and 2, and I also have the, I'm quite anxious, so sorry for mistypes. So I have also one service, Nginx service, and I'll be trying to access this service from a host, so it works. Then I will try to access this service by using the cluster IP from a pod. It works. And then I will try to access the service from a remote client, so over the node port. And again, it works. And if we take a look into the Iptables rules, which we have, you will see that we have no Iptables rules. So maybe I'm hiding those rules. Let's try to add Iptables rule, let's say forward JDrop. And we can see that, oops, we don't have even the Iptables modules installed in the system. And let's check whether we have the, what was the kernel version, whether we have installed NetFilter in the kernel, whether we have compiled it in, and we see that config NetFilter is not set. So it basically means that the NetFilter was compiled out of the kernel. So this talk is going to be about how we made it possible that you can have the service abstraction without Iptables and NetFilter. Okay, let's move back. So before we begin, so why do we want to get rid of Iptables and NetFilter? So on this slide, I have the kernel profile, which I got while doing some network stress testing. And long story short, me and my colleague were trying to connect Docker containers by using IPVLAN instead of the traditional way with the virtual Ethernet pairs. And we were expecting to see much lower latency, but in the end, we didn't see, and we took a look into the kernel to see what's going on. And we saw that a quite huge amount of time, like percentage of total time of packet processing, was spent in Iptables modules and NetFilter modules, which I put in bold. So basically, that cluster which we used for testing, it even didn't have many Iptables rules. It just had some rules which Docker installs by default. And the situation becomes even worse when you have the rules, Iptables rules, which match your traffic. Another reason is reliability of NetFilter and Iptables. So probably many of you got hit by this issue where kubedns was taking 5 seconds to reply to your DNS requests. And the culprit of the issue was that NetFilter had some race conditions which got fixed, but I believe that still many of you are experiencing this issue because you're probably running not recent enough kernel version, and it's understandable because updating the kernel in the large production fleet, let's say, takes time, and also it's kind of risky operation. But also fixing the kernel, it takes time. So to give you the timeline, so I got to the root cause of this issue in 2018 May, and then I submitted some kernel patches to the NetFilter project in August 2018, and those patches got merged by the NetFilter team only in 2019 February. So it took almost half a year to merge the patches and undefined amount of time for distros to backport those patches. So the fix should be available now, but it took a while to make it available. And fun fact is that I was doing some archaeology of this issue, and I found out that first occurrence of this bug was mentioned almost a decade ago. So yeah, so another issue is debuggability. So I would say that it's kind of easy to debug iptable rules when you have just a couple of them. And you can use the packet counters, or you can, I don't know, add a new rule which would log all your packets and you see which rule got exactly hit. But situation becomes more interesting when you have a bit more rules. So in this slide, I tried to place all the iptables rules which were created by Kubeproxy, and I had just 100 services which use the same endpoint. So unfortunately, I didn't manage to put all the rules into a single slide. And to add more fun, Kubeproxy periodically resets the iptables packet counters. So good luck with debugging. So I think I could talk more about what's wrong with the iptables. I think I could spend all slot about this, but let's move on. So let's better understand where's the overhead coming from NetFilter and iptables first. So you don't have to understand anything what is inside those boxes. I just wanted to show you that for each individual packet in the kernel, there are quite a few steps which should be taken. So the orange boxes denotes the execution of the iptables chains, and usually as a user, you install your iptable rules into those chains, and those orange boxes, that's where the execution is taking place. So for instance, if we have the packet being sent from outside somewhere to the pod on the local host, the kernel first has to allocate this SKB, which is a representation of the packet. Then the traffic control takes place, and then all the iptable rules in orange are executed, and all the rules inside those chains. And then the routing decision has to be made, which is denoted in the fib lookup box. And then again, more iptable chains and iptable rules, and finally the packet is being sent to the one end of the virtual Ethernet device, and then the packet enters into the network namespace of the pod. And again, inside that network namespace, because the chains are per network namespace, again, you have to traverse all those chains again. So that's where the latency is coming from. And let's take a look how Kubeproxy takes advantage of those chains. So in this example, we have a simple service, Nginx, of the cluster IP type with the virtual IP allocated by Kubernetes and with 2 endpoints. So first, it installs a generic rule into the pre-routing chain to steer all the traffic, regardless whether it's Kubernetes traffic related or not, into the kube services chain, where the matching for the Kubernetes service takes place. So if the destination is 3.3.3.3, which is the virtual IP of the service, then we enter this service-specific chain, which is called kube-svc Nginx. And in that chain, the endpoint selection is taking place. It is based on the probability, and either Nginx1 or Nginx2 is chosen, and finally in those chains we do the DNAT, which means that we change the destination IP address from the cluster IP to a real IP of the pod, which runs Nginx. So you might start wondering why, oopsie, I think I missed one slide. But you might start wondering in the previous slide whether we can basically bypass those net filter chains somehow, iptables chains, whether we can just jump from the TC ingress directly to the TC egress. And this is possible with the, let me move here, with the technology which is called EBPF. Alternative approach would be just to modify the kernel and to do some changes, Kubernetes specific ones, but I think such approach wouldn't work because the kernel community would not accept such patches. You could also maintain the kernel, your version of the kernel, but I wouldn't recommend you to do that. But luckily we have the technology EBPF, which allows us to jump directly from TC ingress to TC egress in this case. So EBPF is a virtual machine inside the Linux kernel, which allows us to dynamically reprogram the kernel. And let's take an example. So a user can write a little program in the language, which is a subset of the C programming language, then compile it with the CLang, and next it can load the program into the kernel. The kernel verifies the program. It basically checks that the program doesn't crash the kernel, that it terminates, that it doesn't hang the kernel, that it doesn't try to access some memory, out-of-bound memory, or memory from some other processes. And then if it doesn't reject the program, it just compiles the program into a native machine code. And that program can store and access its state from so-called BPF maps. And these maps are can be shared among different programs, and these maps can be accessed by processes running in user space, and also they can be modified. And the execution of eBPF programs is event-driven. And in this example, we have loaded the program at the TC ingress of EF0 device. So it means that when that network interface gets a packet, the following program will be executed. And this little program which I have probably, can you see it? Probably you can see it. So what it does, if the destination of the TCP packet destination port is equal to 80, which is HTTP, just redirect the packet to the interface LXC0, which is of the pod. And if it's not, just then drop the packet. So it's kind of simple. And eBPF is currently probably one of the most active subsystems in the kernel. And it's being maintained by Daniel from the Cilium project together with Alexei from Facebook. And up to this date, there were 268 active contributors. And the adoption is very huge, I would say, and more tech companies are started to look into this technology and to adapt it. And I listed just some prominent users. So for instance, Facebook has recently replaced their load balancer, edge load balancer, which previously was using IPVS, and they replaced it with a new one, which is written with eBPF, and they saw 10x performance improvements. So each request sent to facebook.com is being handled by eBPF program. And also an interesting fact that the original creator of iptables and netfilter, Rusty Russell, has acknowledged eBPF as a technology which should replace the iptables in the future. So yeah, so having this in mind, let's see how we have replaced Kubeproxy with EBPF in the Cilium project. So to replace Kubeproxy, we have to implement all service types which Kubeproxy supports. So first one is the cluster IP. So the cluster IP allows you to access a pod from inside the cluster, either from a pod or from some host local process running in the cluster. And the access, you can access it by using this virtual IP or cluster IP allocated by Kubernetes. Another service type is a node port. So you can, this makes your services accessible from outside. So Kubernetes allocates a special port, and we basically use the node's IP plus that allocated port. And this node port also allows you to access services from inside the cluster. And the third service type, although it's not listed as service type, is external IP. It's very similar to a node port, but except that it allows you to access the services just outside of the cluster to avoid man-in-the-middle attacks. And the access happens through the IP address, which was defined by a user. And the fourth one is load balancer. We don't have to do anything here because usually it's done outside the Kubernetes cluster by cloud provider's load balancer, and they are using the building blocks of the cluster IP node port or external IP. So let's start with the cluster IP. And with the case when a pod tries to reach another pod via cluster IP. So to make this happen, we have to consider two things. So first one is that when a client pod sends a request, we need to check that the destination IP is of some service. And if it is, then we need to select any endpoint of that service. And then we have to do the DNAT, which means that we have to change the destination IP of that packet into the real pod IP, because previously it had the cluster IP, which is a virtual IP. And another thing is for the reverse path of a reply, we have to change the source IP of the reply, because it will be a real pod IP. And the client is expecting to get the reply from this cluster IP. And if we don't change, then the kernel will drop the packet for us. So let's see how we can do that. So again, I have a little BPF program written in pseudocode, English. And basically, that program we attach to the TC ingress of the LXC0, which is the device of the one end of the pod's device, virtual Ethernet pair. And that program does the following. It checks whether destination IP address is in the service EBPF map. Remember, I mentioned that BPF programs can access its state or some data inside the BPF maps and read that data and modify the data. So we have a service map for the services. And then if it's, the service was found, then select the endpoint for the service and then replace the destination IP with that endpoint IP, which is a pod real IP. And then we create two connection tracking entries, again, not in the netfilters connection tracking table, but we have a separate eBPF connection tracking table, which is, again, eBPF map. So for the service, we have, for instance, for this case, we have a service map which contains two entries for two endpoints, because previously we saw that we have two Nginx pod. And the key is basically the cluster IP plus port. And the value is like service ID, endpoint IP address, and endpoint port. And for the connection tracking, again, we have this eBPF map where we have the tuple. The key is a tuple, basically a source part and destination part, and the value is either, depending on the contract entry type, is either the endpoint ID and the service ID, because the first entry is like of the service type, and because we want to make sure that each packet which belongs to the same connection is being routed to the same endpoint, so we have to store the endpoint ID so that subsequent packets could know to which endpoint the packet requests have to be sent. And for the reply, because we have to change back the source IP address, we need to know to which source IP we have to change. So for this, we attach another program which does this reverse NAT translation. And we attach it on the TC ingress of the native device in this example. OK, so how do we update the service maps? So this is relatively simple because we run Cilium agent on each node in the cluster. And this Cilium agent gets, those instances of Cilium agent get notifications from the Kube API server about the services. So basically, we are interested in service object and endpoints object. And once we get those objects, we parse them, and we do the BPF map update, which is a syscall to update the map with a particular file descriptor. So basically, we populate the service entries. OK, so how do we enable the communication from host, not from a pod, but from a host process, which is running not in a pod? And how do we enable the communication via cluster IP? So we could imagine that we have this client, which is running some Go code, and it's doing HTTP GET request. And we could have created a dummy device and installed the IP route rules. That would be similar, I think, what IPVS does, Kubeproxy in the IPVS mode does, but it's not elegant at all. So under the hood, what this client process does when it wants to establish a connection, it does the connect syscall. And there's a special set of EBPF hooks. So it's called EBPF C groups. They are called EBPF C group hooks. And they allow us to attach an EBPF program at that point, at a particular point, and the program is going to execute it just before the TCP or UDP protocol handler in the kernel will handle that particular syscall. So what can we do? We can attach, again, a little BPF program which does a similar thing, but checks the service map, and if it finds that the entry, like the destination IP and port belongs to a service, it can change the destination address and port, but this type not in the packet, but in the socket. And this is super exciting because this is totally transparent to the application, as was in the previous case, but the cost for load balancing is being paid only once, just for the first packet during the connection establishment. And the rest of the flow even will not trigger this BPF program. And recently we have enabled this feature for previous case where we had the pod communicating with another pod via cluster IP. Okay, and we have the same for the connected UDP, and for unconnected UDP, we do similar thing, but for different system calls. So the next one is the node port. This is a bit more complicated. So let's say that we have a node A, which is running Redis pod, and we have node B, which is running Nginx pod. And we have a client somewhere outside our cluster. And the client wants to connect to the Nginx pod via node port, via node IP of the node A and the port of the Nginx service. So it first sends the request to the node A. So again, we attach a little program to the TC ingress of if0. And this time we have this extra step, which is 2.1. We have to do, because node A doesn't run the pod, we have to pass that request to the node B, which runs the destination pod. And before passing, we have to do the SNAT. We have to change the source IP of the request, because otherwise the node B will get a request with the original source IP of the client, and it will reply back to the client. And it will not know that it has to change also the source IP. And remember, I previously mentioned that in such situation, the packet is being dropped because it cannot be recognized by the kernel. So for this reason, we do the SNAT. We change the IP address of the request to a node A IP address, and then we forward the packet. And on the way back, the reply is being sent back to the node A. The node A this time has to do the reverse SNAT, reverse DNAT translation, and finally to redirect this. With this approach, we kind of see two problems. Is the first one that Nginx pod doesn't see the real IP address of the client. And the second problem is that we have this extra hop. So the extra hop from node B to node A, instead of node B sending directly back reply to node A. So to prevent from this situation, Kubernetes has this special service annotation, which is called external traffic policy equal local. What it does, it basically drops a request if the destination node, to which a request was sent first, doesn't run a required pod. But with eBPF, I mentioned that we can do whenever we want with the packet. So nothing prevents us from implementing direct server return for the node port. So what we can do, how we can implement this, we can basically, when we want to forward a packet to a node B, we can append into IP either the service address, so that node B can use this service address when sending back reply to the client instead of node A. So in this example, you see that the client real IP is being preserved. So the Nginx will see the real IP, and then on the way back, the node B will change the source IP to the service IP, and it will redirect directly to the client. So we have solved two problems. So the source IP is being preserved, and we avoid this extra hop. Okay, so the talk is cheap, so let me show you some numbers. So we did some benchmarks on bare metal machines on AWS, connected with 100 gigabit link, and we were running 5.3 kernel, and we used NetPerf's TCP CRR. So what it does, it opens a TCP connection, sends some payload, sends a payload back, and closes the connection. And it measures how long it takes to do this whole transaction. And because I'm showing the latency for you, so lower is better. So first thing to mention is that our eBPF implementation has outperformed both Kubeproxy in IPVS mode and in the Iptables mode. Also, another thing is that we can see that with the number of services, once we have more services, the latency is increasing for the Iptables because of the kube services chain, which I showed you in the beginning. So this chain gets more and more rules, and the packets have to traverse many rules, like instead of doing this hash table-based lookup as we do in eBPF. And another thing is that Iptables actually outperforms IPVS implementation when there's a relatively small number of services. And another benchmark which I would like to show with you is TCP-RR of the NetPerf. This time, the benchmarking suite is reusing the same open connection. And basically, again, eBPF outperforms both IPVS and Iptables. And this time, we don't see this pattern with the Iptables, that the latency increases with the number of services increasing, because we are reusing the same connection. And eBPF DSR has even better performance, lower latency because of the hop being avoided, which I showed in the previous slides. So to recap, I have presented you the replacement of Kubeproxy in eBPF, and this replacement allows you to run the cluster with net filter compiled out without iptable modules, etc. And it gives you a better performance compared to Kubeproxy in both modes, and also it doesn't suffer from slow service updates, which I didn't mention in the beginning, but basically with the iptables you cannot update a single rule, you have to update all the rules. So the more services you have, the longer it takes to update the services. Also reliability, so I would say that our data path is very small, and it's easier to debug it, and it has less lines of code, so the surface for bug is smaller, and also for security issues it's much better. And also we can write the unit tests for the networking code, and it's easier to write than for instance, for the Linux kernel networking. And also, cool thing is that, remember I mentioned that, okay, we had this net filter race condition and it took a while to fix, and also you had to recompile the kernel to redeploy the kernels. And with eBPF, we don't have this. We don't have to do this because we can atomically replace the programs, running programs, without interrupting any connections. And yeah, again, debuggability is much better. Yesterday there was a talk from Nathan from DigitalOcean about debugging Cilium, troubleshooting Cilium. And we have the Cilium monitor tool, which allows us to, which says us exactly why the packet was being dropped, why it went to this pod instead of that pod, and why this decision was taken. So we cannot see this information with the TCP dump. Another thing is compatibility. So the way people configure iptables, they use iptables executable, and recently some distros has switched the backend of iptables. So some distros like Debian, I think they started to use nftables, and it's not compatible with the legacy iptables. So I think in the future we're gonna see quite interesting bug reports. And finally, customization. So with the eBPF, we are flexible what we want to do. We can, as we saw with the node port example, so we can modify the packet and we can implement interesting, like we can, it's up to us how to do the load balancing, so we can implement different load balancing strategies. Okay, so that was it. So I think I got a couple of minutes for questions. So thanks for your attention. If you have some questions, yeah, feel free.
Hi. So I actually asked this at yesterday's DigitalOcean talk, but my main question actually relates more to BPF than it does to Cilium. And you know, with the concept of user space applications, we've done a fairly good job of you know, removing a lot of the risks in running untrusted code. For example, we have sandboxes, seccomp, AppArmor profiles, etc. Now that we're allowing users to basically take untrusted code and run it directly into the kernel environment, what checks are in place to make sure that we don't essentially have a bug end up running in ring 0 and essentially taking over the system inside of the kernel?
Yeah, thanks. That's a very good question. So as I mentioned, we have this eBPF verifier, which does a lot of checks for us. And also, you have to be a privileged user to load the program. So you can disable eBPF in some subsystems, for instance, and you can do it just for networking. So yeah, I hope it answers your question.
Yep, thank you.
On your earlier performance slides, what was the horizontal axis? It says number of services. Is that number of services per node or number of services in the cluster altogether?
So the cluster, so it's a number of services per cluster, but basically what happens is that you have to install all service definitions either for IPVS, Iptables, etc. on each node.
Cool. I think that's all the time we really have for questions.
So if you have more questions, we have a booth. So feel free to come to the booth and ask people questions. And we have some Cilium members which are over there, so they can happy to answer your questions. Yeah, so thanks.